Hi, folks. This is Math 2250, and this is our lecture that is going to take place in lieu of the lecture that was supposed to be on Tuesday, September 7th, because as I already announced, I observed all the Jewish holidays. There'll be a few more days when I have to be away, and I will record lectures to compensate for that. So we're going to get started. I'm going to pull up a Zoom whiteboard and go through most of, but not all, of section 1.2. And we will finish off 1.2 on Thursday and move on to the section after that. Okay, so let me pull up the whiteboard. Okay, so section 1.2, which is about row reduction. And the echelon forms, so-called echelon forms of a matrix. Okay, so let's talk about echelon form. Using the term echelon form each time, writing it out is a little tedious, so I'm going to sort of just write EF. Okay, so a matrix is in echelon form when, so remember, a matrix is a table of numbers. An m by n matrix has m rows and n columns. And I want to give criteria for saying when it has a special form called echelon form. And here are the three criteria. So the first is that all rows consisting entirely of zeros are at the bottom. In other words, if you have a row consisting entirely of zeros, then every row below it consists entirely of zeros. Okay, the second condition is that the leading, this is a little awkward to state, the leading non-zero entry or entries of the rows go from left to right when you move down the rows. So let me just illustrate that point a little bit. Suppose I have, say, 0, 0, and then some non-leading entry, which I'll just indicate by an asterisk and so on. Then in the next row, you would have the first non-zero entry would have to occur to the right of the non-zero entry of the row above it. So as you move down, the non-zero, the leading terms, the non-zero leading terms move to the right. Okay, and then the third condition is that all entries in a column which are below a non-zero leading entry are 0. So what I mean is, suppose I have Oh, I don't know. Let's suppose I have something that looks like this: 0, 0, 0, 0 star, etc. Everything below each non-zero leading entry is going to be 0 in that column. You might hear the dogs in the background. Okay, so let me save this slide and clear the screen. Okay, so we just made a description or a definition of what it means to be in echelon form. There's an additional type of form, which is something above and beyond echelon form, called reduced echelon form, which in most cases is more convenient. So this is going to be echelon form plus some additional conditions. So let me state it. This is echelon form, and in addition, we have steps, conditions 4 and 5. So the condition 4 is that each non-zero leading entry in a row, oops, my handwriting sucks. I shouldn't say each, I should say the non-zero leading entry in any row, which is not 0, is equal to 1. So the non-zero leading entry in a row that has something which is non-zero in it, that leading entry is 1. And then 5, in the columns which have a non-zero leading row entry have entries which are 0 except for that leading entry. This is really poorly stated. Let's say, let me just say it this way. In the column, let me restate this. This sucks. This is not clear. All entries in a column above and below a non-zero leading entry, I'll just say leading entry, are 0. So everything but the leading entry in the column is 0. So I'm going to give examples in a moment. And it's important to keep the examples in mind because this is just a list of conditions. But let me just say it this way, that the location of the non-zero leading entry has a name. It's called the pivot location. And the column with a pivot location is called the pivot column. Now, if any of this is confusing, it should become clear in a moment when I do an example, okay? I'm going to give you some examples of matrices that are in echelon form and in reduced echelon form. Okay, so I'm going to clear the screen again. Okay, so let's consider the following example. So let me write down a matrix: 1, 0, 3, 4, 5, 0, 1, 1, 2, 0, and then 0, 0, 0, 0, 0. So this is a 3 by 5 matrix. It's got 3 rows and 5 columns. So the leading entry, the zeros are on the bottom. There's a row of zeros on the bottom, which is good. That was the first condition. The leading entry in the first, the leading entries, which are non-zero, as you move across down, are moving from left to right. And here are the 2 non-zero leading entries. So the pivots occur in the first row and first row, first column, and in the second row, second column in this case. There are no other pivot locations. So this is in echelon form, and in fact, it's let me change this example. Let's change the 0 so that it's non-zero, so it's a 2. So then it wouldn't be in reduced echelon form. It would be in just echelon form, because the entry above the second pivot in the second column, which is a pivot column, this entry of 2 is non-zero, right? So so this is in echelon form, but not reduced echelon form. Here's another example. Suppose I take 1, 0, 3, 4, 5, and then I get 0, 1, 1, 2, 0. It's the thing I just corrected myself on. So this is in reduced echelon form because we have the pivots. I'm circling the pivot locations. The pivots are 1. The pivot locations have entry 1, and above and below the pivots, you have 0 entries. So this is in reduced echelon form. Here's another example of reduced echelon form. Suppose I take 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 4, and then 0, 0, 0, 0. So the 3 pivot locations I'm circling, and above and below the pivots, I have 0 entries. The pivots are moving from left to right as I scan the matrix as I go. If I scan along the matrix from left to right, the pivots are moving down and to the right. So that's in reduced echelon form. Okay, so those are some examples. Not every matrix is obviously in reduced echelon form. So you have to sort of recognize when a matrix is in reduced epsilon form or in ordinary echelon form. So here is the basic fact, which comes about from what we talked about in the previous lecture, that you can do elementary row operations to always put a matrix in echelon form or into reduced echelon form. And I'm going to give you the algorithm in a moment. Let me just state the result. Okay, so let's do that. So here's the row reduction fact. Any matrix can be transformed to one which is in echelon form or even better reduced echelon form by a sequence, by a finite sequence, only have to do it finitely many times, of elementary row operations. Recall that there were 3 row operations that we can talk about. There is the row operation, which allows us to switch rows, exchange rows. There was a row operation which added a multiple of one row to another row, a scalar multiple of one row to another row. And the last operation we can discuss is that you can rescale a row by a scalar, a non-zero scalar, I should have said. Okay, so I'm going to now talk about the so-called row reduction algorithm. So that's now. Let me make a line on the page. Okay, so so here's the row reduction algorithm. It's kind of clunky to state, but it becomes clear when you implement it. Let me state the clunky statements, okay? So here are the steps in the process. So step one, let's find the leftmost non-zero column. It's often the first column, but it might not be the first column. It could be the first column consists entirely of zeros, in which case you move on to the second column until you get to a column which has a non-zero entry. And the leftmost non-zero column will be a pivot column. This will be a pivot column. Okay, so that's step one. You've identified the leftmost non-zero column. Step two. Okay, so now, if necessary, you can exchange the rows. Exchange rows. So the non-zero entry, or a non-zero entry, I should say. Let me say A, because there could be more than one. Oops, handwriting. In the pivot column that you've identified in step one is at the top, is in pivot position. I'll just write it that way. It's at the top in the first instance. This will become clear in a moment, okay? Step three is we clear the entries below the pivot using elementary row ops. Clear entries below that pivot using elementary row ops. Okay, step four. So we cover the row that contains the pivot now and all rows above it. But in the first time, you won't. You're not going to see that. So cover the rows. Cover the row containing the pivot. The pivot. And all rows above it. And then apply and then iterate again. So repeat the above steps until you can't go any further. So until the matrix is in echelon form. Okay, so now this gives you a matrix in echelon form. Okay, and we'll do an example in a moment. I just want to mention further steps then to get the matrix in reduced echelon form. Step 5 is rescale the rows containing the pivot so that pivot entries are equal to 1. And then step 6, clear entries above the pivots with elementary row operations. Okay, so that when you do that, you'll get, when you do all of this, you're going to get reduced echelon form. Okay, so that's a lot of writing and it's kind of obscure. So I think it's best if we just go ahead and do some examples. Okay, so that's what I'm going to. So here is a concrete example. So we have a matrix. It's a 2x4 matrix, 0, 1, -6, 5, 1, -2, 7, -4. So I want to follow the format of the algorithm. So I look for the first non-zero column in my matrix, and that turns out to be the first column. So that's step 1. And then I switch the rows so that I can get the non-zero entry in that column to the top. So what I'm going to do is I'm going to apply the row operation, which exchanges row 1 with row 2. So that's what indicates exchange row 1 with row 2. So that means I get 1 -2, 7 -4. And then I get 0, 1, -6, 5. Okay, that's pretty simple. Now, it turns out that this matrix, we can identify it's already in, it's in echelon form now, just by doing that one operation. And here are the pivot entries. The pivot entries are also 1, but the matrix is not in reduced echelon form. To get it into reduced echelon form, we have to clear the entries above the pivots to make them 0. So the only problematic entry is the one indicated in blue here. We have to get rid of the -2. So to do that, what I'm going to do is I'm going to replace row 1 with row 1 plus twice row 2, because if I add twice row 2 to row 1, what happens? So adding twice 0 to 1 gives me 1. Adding twice 1 to -2 gives me 0. Adding twice -6 to 7 gives me 7 - 12, which is -5. Adding 10 to -4 gives me 6. And then we have 0, 1, -6, 5. I'm going to circle the pivot entries again. This is in reduced echelon form now. There's no further, we can't go any further with this. We're done. Okay, so that's like a simple example that one can, easily compute. Usually, the examples are not so simple and they require a great deal of steps. This only required 2 steps, 2 operations, 2 row operations to get into reduced echelon form. And the next example will require, I believe, 1, 2, 3, 4, 5, 6, 7 steps. Okay, so let me clear the screen for that. Okay, so I'm going to write a little smaller for this example. So I got 1, 1, 1, 2, 2, 3, 1, 3, then 1, -1, -2, -6. And the problem is to get it into reduced echelon form. So I look for the first non-zero column, which is the first column in this case. So, and then I don't need to switch rows because the first entry in the first column is non-zero. So this is going to end up being a pivot entry, this one that I've underlined. So what I'm going to do is I'm going to clear the entries below that one. And how do I do that? Well, I'm doing it one elementary row operation at a time. So I want to clear the 2 in the second row. So that means I'm going to take the second row and replace it by row 2 minus twice row 1. Okay, what does that give me? Well, row 1, row 3 stay the same. But what happens to row 2? It becomes 0, 1, minus 1, minus 1, I believe. Is that right? Yeah, 3 minus 4 is minus, yeah, this is correct. And then we get 1, minus 1, minus 2, minus 6. Okay, so that's the first step. So now I have to clear the entry that I'm going to underline called 1. Okay, I got to get rid of that. Actually, let me not underline it. So I want to clear that 1. So what I could do is take row 3 in the matrix and subtract row 1 from it. So that's row 3. Row 3 gets transformed to row 3 minus row 1. Okay, so what does that give me? It gives me 1, 1, 1, 2, 0, 1, minus 1, minus 1, and then what? 0, minus 2, minus 3, and I think minus 8. Okay. All right, so now I have identified, I gotten the first column in good shape. There's only one non-zero entry in that column. I'm circling the pivot location. Okay, so now I cover the matrix, I cover the first row, and then I want to apply the same algorithm. So I look after covering the first row, which I cannot seem to do with my whiteboard. I identify the first non-zero column of the submatrix, which will be the second column, right? So I'm going to identify that's going to be the pivot location in the next step. Okay, so the 1 that I've just underlined, okay, which I'm going to remove the underline. So what I'm going to do is I want to get rid of the entries below that 1. I can circle that 1 because it's going to be the pivot. Okay, so what do is I want to take the row 3 and get rid of the minus 2 below that 1. So I can replace row 3. I can transform it to row 3 plus twice row 2. And what does that give me? It gives me 1, 1, 1, 2, 0, 1, minus 1, minus 1, and then 0, 0, minus 5, minus 10. Let me continue to circle the pivot locations. Okay, so you can see that this is now in echelon form. So this is in echelon form, but it's not in reduced echelon form. To get it in reduced echelon form, we have to continue. Okay, and so I can first of all note by wiping out the first 2 rows, I have a non-zero entry in the remaining submatrix, which is a 1/4 matrix. The minus 5 is going to be a non-zero entry. And I'm trying to get this in reduced echelon form, so I have to make that minus 5 a 1 by rescaling. So I can take row 3 and replace it by minus a 5th row 3. And that gives me 1, 1, 1, 2, 0, 1, minus 1, minus 1, 0, 0, 1, 2. And I'm going to circle the pivot locations. We're not done because the entries above the pivot locations are non-zero. We have to apply 3 more operations to get rid of the entries above the pivots. So the first step is to get rid of the entry above the second pivot, which is a 1. And you can see this one here. I'm using my magic wand to indicate the 1. So let's get rid of that 1. How do we do it? We can take row 1 and replace it by row 1 minus row 2. What does that give me? That gives me, I believe, 1, 0, 2, 3, 0, 1, minus 1, minus 1, 0, 0, 1, 2. It's important to only do one operation at a time, generally, because if you do more than one at one time, you're likely to make a mistake. The operations do not commute with one another, and that's sort of the problem. We'll see that later, why that's the case. Okay, so let me circle the pivot locations. We still have two entries which are above my third pivot, these two entries here, which my magic wand is indicating. And I'm going to get rid of them. And how am I going to do that? I'm going to take row 1 and subtract twice row 3 from it to get rid of that entry, which is a 2. So what do I get? I get 1, 0, 0, minus 1, 0, 1, minus 1, minus 1, 0, 0, 1, 2. We're nearly done. We're in the home stretch. I'm circling the pivot locations. I now have to just get rid of the entry which is labeled minus 1. And I can do that simply by replacing row 2 by row 2 plus row 3. Oops, that plus was not a good plus. So what do I get when I do that? I get 1, 0, 0, minus 1, 0, 1, 0, 1, and then 0, 0, 1, 2. So here are the 3 pivots. The entries above and below the pivots are all 0 entries. This matrix is in reduced echelon form. And we are done with the example. So how does this echelon form help us in solving linear systems? So let's just take let's take an example, a concrete example. So let's take the system which has 3 variables, x1 minus 5, x3 equals 1, and then x2 plus x3 equals 4. And then, that's the, and there's also an x4, it's 4 variables, right? There are 4 variables, x1, x2, x3, x4. Is that right? No, x1, x2, x3, that's a mistake. Okay, so we have 3 variables, it's a 3 variable system. And maybe I have 0 equals 0 is also an equation, which is not a very interesting equation. But when I write down the matrix of the system, it becomes simply 1, 0, because there's no x2 in the first equation, minus 5. The augmented matrix has a 1 in the last column, in the first entry in the last column. And then we have 0, 1, 1, 4, because the x2 and x3 coefficients are 1. And then we have a row of zeros. Okay, so here we go. That's the augmented matrix. All right, so I can put a wall here, just indicate it's an augmented matrix. And so let's circle the pivot locations. There are 2 pivots in this matrix, and the 2 pivots, the pivots correspond to the variables x1 and x2, because they are in this corresponds to 1 times x1, and this corresponds to 1 times x2 when you write out the equation. So the pivots correspond to the variables x1 and x2, and these are called the basic variables in the book. They might also be called the dependent variables by some. So the pivots correspond to dependent variables, and the remaining variables, the non-pivot variables, pivot locations correspond to, in this case, to the remaining variable, which is x3, and that is a free variable. So you have dependent variables and you have free variables, or basic variables and free variables. And to see why we're calling it that, we write the dependent variables in terms of the free ones. There's only one free one in this case. Okay, so what do we write? Let's go back to the equation. It's already in echelon form, reduced echelon form, this system. So we can think of x1 as 1 plus 5 times x3. I've gotten the free variable on the right, and x2 is equal to 4 minus x3. And that's the entire solution of the system. We can think of x3, think of x3 as any real number, and x1 and x2 are determined by your choice of x3. So another way to write this, which I prefer to do it, is to rename the free variable x3 by the symbol t. And then we can think of x1 as equal to 1 plus 5t, x2 as equal to 4 minus t, and x3 as equal to t. So this would solve the entire system. If you have Math 2030, if you've had that, you'll notice that this is the equation of a line in R3, right? If you've had Math 2030. So this is a way of specifying a line in three-dimensional space. Okay, let me do one more example today of this kind of rewriting, and we'll call it a day. We're not done with section 1.2. We'll finish that up on Thursday. So let me clear the screen. Okay, so here's another example. 1, 0, 2, 0, 1, 1. So this is this, I'm not going to write out the system. I'll just write down the augmented matrix, 0, 1, 3, 0, 1, 4, and then 0, 0, 0, 1, 0, 3. And what are the variables here? Well, this is going to be, there are 5 variables, x1, x2, x3, x4, x5. That's the number of columns to the left of the wall of the augmented matrix. Oh, that should be a 5, sorry. Okay, so, and which are let's circle the pivots. This is already going to be in reduced echelon form. There are 3 pivots. Here they are circled, and they correspond, the pivot variables, which are the same as the dependent ones. Oops, the word variables is not spelled very well. These are x1, x2, and x4. And the free variables are the remaining ones. That would be x3 and x5. Oops. So we write the equation. If we were to write out the equations, the first equation would be x1 plus twice x3 plus x5 equals 1, correct? So you can write x1 as 1 minus 2x3 minus x5. I'm writing the dependent variable x1 in terms of the free variables. Likewise, by a similar game, we can write x2, sorry, x2, not x3, but x2 as 4 minus 3x3 minus x5, and then we have x4, the remaining dependent variable, is going to be given by the number 3. So what I propose in writing the solutions is to set x3 equal to the letter S and x5 equal to the letter T. And then the remaining variables you have are x1 equals 1 minus 2s minus t, x2 equals 4 minus 3s minus t, x3 equals s, x4 equals 3, and x5 equals t. And this specifies the entire set of solutions where s and t are any real numbers. So, so for any pair of real numbers, we get a solution to the system. And I don't want to go too much into it now, but this would be a plane, a two-dimensional plane in five-dimensional space. That's what it would look like if you could picture that. Anyway, that's all I want to cover today. This was a long enough lecture for a Zoom lecture, and I hope I was clear. Have a good one.